Hi, everyone. We've been discussing quantum mechanics, and we found that um, every system or particle can be described by a wave function, and wave functions have to be solutions to the Schrodinger equation. Okay? Furthermore, we found that for problems where the potential energy doesn't depend on time, but only depends on position, that we can use a simplified form of the wave equation called the time-independent Schrodinger equation to find energy states. Perfect. And then last time we also looked at the wave function for a free particle and found a function that would satisfy the time-independent Schrodinger equation. Today we're going to build on that and look at a situation in which free particles are incident on a potential step. And we'll see we'll be able to use quantum mechanics to describe the whole thing. So that's what we're going to do. You'll see that there's a little more math in this than in some of our previous lectures. And furthermore, we'll introduce some kind of new techniques. They're new to us, but they're very familiar to people who work with waves. Okay? It won't be so bad, and it'll put us in a good stead for the rest of our discussion of quantum mechanics. Here, let's go to an outline. All right. So as I said, we've already talked about the time-independent Schrodinger equation, and we talked about free particles. And we'll go over this again in just a moment. For today, I want to talk about the step potential problem. This one, where particles are incident on a potential step, and we'd like to know what happens to them. As we talk about this, it'll be helpful to first describe a classical analog, okay? So that we can compare what happens to quantum particles to the classical analog that probably we have a good intuition of. We'll look at two cases. The case where the energy of the particle is greater than the height of the barrier. And the second is the case where the energy of the particle is less than the height of the barrier. Finally, for that first case of energy greater than the height of the barrier, we'll work out transmission and reflection coefficients, which will tell us the probability that a particle is reflected or transmitted at the barrier. Okay? Well, that's what we're going to do. Okay. Here, let's quickly review the time-independent Schrodinger equation. We said that for energy states, the wave function can be written in a particular form. It can be broken apart into two functions, one that depends only on position and a second that depends only on time. And usually, we only need to find the part of the wave function that depends on position to learn everything we need to know about our particle. Okay? Furthermore, that first part has to solve a simplified form of Schrodinger's equation called the time-independent Schrodinger equation. So minus h bar squared over 2m times the second derivative of psi with respect to x is equal to E minus U times psi. Okay? Okay. The simplest system that we can investigate is that of a free particle where the potential energy is constant, maybe even equal to 0. All right? If we substitute free particle state. And last time we showed that the following is a solution to the time-independent Schrodinger equation. Okay? We found this is a solution provided that k is equal to the square root of 2 times m times e minus u0 all over h bar. And this was consistent with the relationship P equals h bar k and with the de Broglie relationship. Okay? All right. Something that we didn't mention is that there's also another solution. Okay? We could also let psi equal b e to the minus I kx. And then one can show very easily that this second form is also a solution to Schrodinger's equation. If you want, you can pause the video, go ahead and substitute this in, and you'll see in a moment that that's true. Okay? Because of this, the most general solution is actually a combination of these two. There we are. So the most general free particle state looks like this. It's a linear combination of A e to the ikx and B e to the minus ikx. Well, it's given us the sum here. And there's something really interesting about this. If we were to put the time-dependent part back in, we would see immediately that the first term, e to the ikx, that describes a wave moving to the right, to positive x. Whereas this term here, we'd see as describes a wave moving to the left. And just like in the sound tube, we can have superpositions of waves moving to the right and waves moving to the left. And any linear combination of that will solve Schrodinger's equation for a particular value of k. Okay? It's hard to have a mental picture of something being a superposition of a particle moving to the right and particle moving to the left, but just think of the wave picture, and maybe that'll make sense. All right, let's stop here, and then we'll go to our important problem.